Our next unit is energy, and this is actually a pretty big one. We'll end up doing energy, work, and power, but we're going to start with the energy. I'm going to give you some definitions, and then we'll get into 3 examples, just one for each type of energy. So I'm just going to apologize in advance, there are a lot of definitions here. You do, however, have the guided notes in your packet, so just follow along with those. Okay, the first thing is spring preload. This is measured by the vertical intercept on a spring force versus stretch graph. So this is the graph that we saw in the lab. It represents the minimum force needed to stretch or compress the spring. The symbol for spring preload is an F with a subscript of 0. And because this is a force, the units are newtons. And that's a 0. Sorry if that's bad. So in other words, the spring preload is telling you how much force you need to initially get that spring to start moving, either compressing or stretching. The higher the spring preload, the more force it's going to take. So when you were doing the lab, if you had the white or the green spring, that probably took a lot more force to pull apart than it would for, say, the blue or the red spring. The next thing we have is the spring constant, and this is measured by the slope of your spring force versus stretch graph. So again, we saw this in the lab. This tells you the stiffness of a spring once it has been stretched or compressed. You can add as well. The symbol for spring constant is a lowercase k, so either lowercase k, you'll see me probably write it like that a lot. And the units for spring constant are the same units as the slope. We had force on the y-axis and stretch on the x-axis. So these units are newtons over meters. So the spring constant, the higher the spring constant, the stiffer the spring is. So something like a slinky, which is a spring, would have a very low spring constant and a very low spring preload. Doesn't take much to stretch or compress the slinky, and it also doesn't take much, it's not very stiff at all. So spring constant and spring preload are the 2 values that came out of the graph, just the plain old graph with the vertical intercept and the slope. Okay, next we have an ideal spring. This is a spring that has a preload of 0, meaning that almost any force will cause the spring to deform. And when I say deform, I mean either stretch or compress. Ideal springs are going to comprise about 95% of the problems that we do, so assume that most of them are ideal unless it specifies a spring preload. So this brings us to spring force, which is Hooke's law. And the equation for Hooke's law: spring force equals K delta X plus F0. And we saw that in the lab. This should have been from the 3-step math model. So Fs is the spring force. K is the spring constant, 70 degrees and sunny. Delta X is the stretch or compression. And F0 is your spring preload. So that's Hooke's law. Again, I know we said we're doing energy. This is really the only new force equation we'll have, and it's not used that much, but it will pop up here and there. Okay, so next, energy. All energy is the ability to make something happen. And we're going to start with elastic potential energy. The only types of energy we'll be dealing with right now are mechanical. Mechanical means movement, or something you could see. So we're not going to look at chemical energy. We're not going to look at electrical energy. Right now we're just going to deal with mechanical energy. So the first type, again, we saw from the spring lab, is elastic potential energy. And this is measured by the area under a spring force versus stretch graph. It's the amount of energy stored in a stretched or compressed spring. The symbol for elastic potential energy is a capital E with a lowercase el. So it looks like eel. The units for energy are joules, and the equation EEL equals 1/2 K delta X squared plus F sub 0 delta X. So the EEL is your elastic potential energy. Your K is the spring constant. Delta X is the stretch or compression. And that's the same for this delta X right here. And F0 again is the spring preload. For ideal springs only, ideal spring, remember, is a spring preload of 0. This whole term goes away. So EEL equals 1/2 K delta X squared. And remember, I said that 95% of our springs will be ideal. So this will be the main equation that we're using when we deal with elastic potential energy. This is all the information you're going to need to do worksheet 1. So there's only 2 definitions after this, and then I do an example for each type of energy. So 3 examples, 2 definitions, but it's a lot shorter than it sounds. But again, worksheet 1 only deals with elastic potential energy and Hooke's law. So all of the information for that is right here. Just finish up with the last 2 definitions and 3 examples, and then we'll be able to do more practice with those. So let's go to the next 2. Okay, gravitational potential energy is the energy stored due to an object's height above the Earth or any really set base level. So in other words, once you determine where the bottom is, anything above that bottom level is going to have gravitational potential energy. The symbol for gravitational potential energy is a capital E with a subscript of G. The units are, again, joules. And the equation for gravitational potential energy, Eg equals mgh, where h is the height above the base level, g is our gravitational acceleration, or acceleration due to gravity, on Earth, 9.8 newtons per kilogram, or meters per second squared. And m is your mass. Eg is this gravitational potential energy. Fairly straightforward equation. The next type of energy we have, and the last one that we'll be looking at, is kinetic energy. Kinetic energy is energy stored in an object's motion. Symbol for kinetic energy is a capital E with a subscript of a little k. Again, the units are joules because this is energy. Equation for kinetic energy, Ek equals 1/2 mv squared. So this is your speed, m is your mass, and Ek is the kinetic energy. So 3 types of energy that we'll be dealing with. We will see how they relate when we get to conservation of energy. All you need to really know right now are the 3 different types. And I'm going to do the examples in your packet. So I've got 3 examples. I'll do all 3 of those, and it's just each one using the equation. One thing that I do want to add is what's inside a joule, and this is not in your, you should know this. A joule, so that's the big J, is equal to a Newton times a meter. And this came out with the lab for the spring force versus stretch. You had the force on the y-axis, your stretch on the x-axis, and you had your graph. When you take the area of this graph, area of the triangle and the rectangle. So the area of the triangle was 1/2 base times height. Those units were Newton times meters. The area of the rectangle was just base times height. Again, those units were newtons times meters. So the unit for energy is a joule. Breaking down a joule, you get a Newton times a meter, or a Newton meter. Okay, so the first example tells us that a 54 kilogram student running down the halls has 1760 joules of energy stored in her motion. What is her speed? So since this is energy due to motion, we're going to be dealing with kinetic energy. This is a very, very simple problem. Diagram, you have someone just running down the hallway. You do want to do diagrams for these. Given information, we know that the mass is 54 kilograms, that the kinetic energy, Ek, is 1760 joules, and we're looking for speed. So, dealing with kinetic energy, Ek equals 1/2 mv squared. Isolating for v, we get 2 Ek over m equals v squared. 2 times 1760 joules divided by the mass, 54 kilograms, equals V squared. We get 65.1, keeps on going, meters squared per second squared equaling V squared. Taking the square root of that, 8.07 meters per second equals V. This is 2 sig figs, so the speed is approximately 8.1 meters per second. Simple problem. Just getting used to using the equation. I'm just going to do the next two using the other two equations, and then that'll be it. So example 2, a 0.350 kilogram bottle of Gatorade sits atop the bleachers. If there are 24 joules of gravitational potential energy, how high are the bleachers? So here we've got bleachers. We've got a Gatorade bottle sitting at the top of the bleachers. And the only thing you really need to do differently with gravitational potential energy problems is identify your base level. So I usually do that with a dotted line, and I just label it base level. And this is so that you have, I guess, a reference point for where you're measuring the height from. Our given information here is, let's see, the mass of the Gatorade bottle is 0.350 kilograms, and the gravitational potential energy is 24.0 joules. And we are looking for height. Again, easy equation, EG equals mgh. So EG over mg gives me height. 24 joules divided by the mass, 0.350 kilograms, times 9.8 newtons per kilogram equals height. And we get 6.85, keeps on going, meters for the height. So this was 3 sig figs. So the height is approximately 6.86 meters. And then one more example. This one's using elastic potential energy. We have a force of 35 newtons stretching an ideal spring 0.04 meters. Part A, what is the spring constant? Part B, how much energy is stored in the spring? So the spring diagrams are simple. We show a spring, and then the spring in this case is getting stretched. So I show the spring stretched. So what you want to do is show the spring when it's relaxed. Relaxed means not stretched or compressed. It's when it's in equilibrium. And then show it when it's either stretched or compressed. So this distance right here is your delta x. Given information, we know that the spring force, Fs, is 35 newtons. We know that the delta x is 0.04 meters. It's an ideal spring, so F0 is 0 newtons. Unless it says otherwise, unless it gives you a spring preload, you can assume that these are all ideal springs. And what are we looking for? We are looking for the spring constant K and how much energy is stored in the spring, EEL. Given spring force and delta x, the only equation that has that in it is Hooke's law. Spring force equals K delta x. Because spring preload is 0, this is plus F0, so that goes away. So my spring force divided by my stretch will give me my spring constant. 35 newtons divided by 0.04 meters equals K. 35 divided by 0.04 is 875 newtons per meter. And this has 2 sig figs. So K is about 880 newtons per meter. Simple enough. Part B, sorry about that. Part B is asking for how much energy is stored in the spring. So this is our elastic potential energy, EEL, which equals 1/2 K delta x squared. ideal springs, we can just stop here again because there is no spring preload. We just found K in part A, we were given delta X, so this equals 1/2, using the unrounded number, 875 newtons per meter times 0.04 meters squared. And multiplying these together, we get 0.7 joules. 2 sig figs, EEL equals 0.70 joules. So that's how we use the 3 main equations, plus a little bit of Hooke's law in the third example. There are 8 practice problems afterwards in your packet, so go ahead and just work on those. It's just, again, getting you used to using these equations before we start making them a little bit more complicated.